Hello everyone, this is Aashish Adhikari from Oregon State University. Today I will be presenting my work on improving data center peak saving with deep reinforcement learning. Let's get started. The goal of this work is to reduce the energy cost incurred at data centers. Data centers pay millions of dollars each year in electricity bills, and reducing a small percentage also amounts to a large saving in terms of dollars. Many prior works focus on ways to reduce the total energy consumption of the data centers. However, that is not enough, since the total energy cost consists not only of consumption cost, but also of the peak demand cost. The energy consumption cost is proportional to the amount of energy consumed, but the peak demand cost is not. Next, we'll see how the peak demand cost is defined and why this definition matters. Power companies define a period of large power demand within each day as the peak demand period. Here, 6 p.m. to 12 midnight represents that peak period and is a typical range used in practice. Within each peak period, a slot, typically of 15 minutes, is considered a peak slot. For each such slot, the average power demand is calculated, and at the end of the month, a maximum of all such slots is taken as power max. Then, power max is multiplied with a predefined per unit peak power cost to get the peak demand cost for the month. Shown here are the typical values used for per unit consumption cost and per unit peak demand cost. This definition of the peak demand cost is significant because the data center that uses less energy can actually end up paying more than the data center that uses more energy. In the example shown here, data center A used less energy but has a total energy cost more than that of data center B. Many prior works have illustrated this issue. The reason this happens is because the per unit peak demand cost is several folds larger than the per unit energy cost. One solution is peak saving, where we intend to reduce the power max of the month by using an auxiliary source of energy such as a battery. On the screen, the green section of the peak corresponds to the amount of energy fulfilled by the battery that helps to bring down the peak of the power demand during the peak period. The reason why batteries are preferred for peak saving is because data centers already have large batteries available on site for fault tolerance. Thus, using those batteries for peak saving does not incur any additional buying cost. There are several prior works on peak saving using batteries, but they make many assumptions. Accurate prediction of future demand, static policy learning, incomplete cost models are some of those assumptions. We exclude such assumptions from our work. We propose to formulate the data center peak saving task as an energy arbitration problem in a Markov decision process, or an MDP. First, we define an MDP for a data center using the resource usage trace from Google. We consider the 1-month period data as one episode for the MDP. Then, we use a deep reinforcement learning method to learn how to perform efficient energy arbitration at each step of the episode. Later, we will see the feasibility of a policy that incurs a cost significantly less than the case when no peak saving is done. An MDP can be defined with 4 entities: the states of the MDP, the actions that can be taken in those states, the transition function that defines the probability of reaching any next state from the current state given an action to take, and the reward function that defines how good it is to take an action A in a particular state. Here, we use the last 24 demand values alongside several other variables so on from the environment as the state. We use a set of 10 discrete actions that range from 0 to 1. Each action A represents what amount of demand in the next step should be fulfilled by the utility. An MDP also has a transition function, but this will be irrelevant for our work as we use model-free reinforcement learning and thus do not use a transition function. While an MDP requires a reward function, our task at hand has a cost function, and we will later see how we use this cost function with a tweak in place of a reward function to learn a policy. Previously, we saw that the consumption cost for a month was the total units consumed in a month times the per unit energy cost. However, here we calculate the consumption cost at each time step corresponding to the action taken in that step by the agent. Also, the peak demand cost required taking a maximum among all the slot averages. Now, this definition does not work when we want to associate a peak demand cost to each time steps action. We attribute only the peak demand increment to the action taken. We also take into account two extra costs for each action. We estimate how much degradation the battery incurs when it is used for peak saving and add it to the cost of the action. For this, we use an empirical model as shown on the slide for a better estimation than theoretical models. We also consider the cost corresponding to the refueling of the battery after each usage. Hence, the total cost is a sum of four different costs. In reinforcement learning, agents learn to optimize an objective using a reward function. However, we have generated a cost function. We will see later how this cost function can be used in place of the reward function. There are some challenges inherent in learning a policy in an environment like ours. First, the reward function is non-smooth because an action can suddenly create a spike in the cost. Second, two actions that correspond to the same peak demand value do not have equal effect in the cost. And the third is that the reward is very sparse and most time steps have a negligible cost in comparison to the maximum cost in any step of the episode. We just saw the MDP formulation of a data center. Next, we will see how to train a reinforcement learning agent to learn a good policy for this energy arbitration task. Q-learning is a tabular reinforcement learning algorithm that is used to estimate how good it is to take an action A in state S. It is very popular in literature. However, such tabular reinforcement learning algorithms are not feasible for a problem like ours, where the state can take infinitely many values. The size of the Q-table gets infinitely large, and good approximation cannot be made for the Q values. This issue is also referred to as the curse of dimensionality in the machine learning domain. We thus resort to using a function approximation method called deep Q-learning. Deep Q-learning, or DQN, approximates the Q values for different discrete actions for a given state. It can be viewed as a modification of the Q-learning algorithm that we saw earlier. The vanilla DQN algorithm looks as shown on the screen. However, the vanilla variant of DQN does not learn well in practice. We will use a variant of DQN called dueling DQN with some additional tweaks for our problem. The proposed agent in our work has a set of tweaks as shown on the screen. Next, we will see these additions one by one. We use a neural network as a function approximator for the Q value to avoid the curse of dimensionality. The network will output n set of values for n different actions that the agent can take in the input state. We also use a target network for smooth learning. It has been shown in literature that using a target network to keep the gradient descent targets stationary over time prevents divergence of training and makes convergence faster. Since the transition samples are generated one after the other in an episode, they are temporally correlated. However, supervised learning assumes that training samples are IIDs. Hence, to avoid training the network with correlated samples, we use a uniform replay buffer, which is used at each step to sample a mini batch of training data that are not correlated. We also make use of a dueling architecture such that for each state S, the network estimates the state value and the advantage of choosing each action from the action set before finally giving the Q values of different actions as the output. Also, as we have a cost function instead of a reward function, we replace every maximizing operation in the DQN algorithm with a minimizing operation. This inherently makes this learning objective a minimizing task. This is what the full unrolled version of the algorithm with the tweaks looks like. Shown are the hyperparameters used for training and the total steps the agent took to obtain the results. The graph shown is a training graph for the agent. The y-axis represents the cost, but in an upside-down fashion. This is the test graph that shows the minimum cost obtained at 1500th episode. The curve shows jitter because of the non-smooth nature of the training objective. There are three distinct baselines used for this work. The first is a random agent that takes random action at each step of the episode. We averaged the performance of the random agent over 10 episodes. Next is the utility agent, which is the equivalent of not performing any peak shaving. Third is the fixed agent that is taken from a collection of 8 different agents. For this agent, we first choose 8 multiples of the median peak demand of the whole dataset. Then, for each of these values, over the whole month, if the demand in any step goes below this value, we use the battery to fulfill that extra demand. Else, we use the power utility. We report the best among 8 such agents as the fixed agent. Notice that the fixed agent is fed the information from the future through the median of the demand. Shown are the results for the baselines together with the result for the proposed agent. The proposed agent outperforms no peak shaving method by 33.9%. It also significantly outperforms the best fixed agent. The 33.9% gain achieved was only for one cluster. A large corporation that has thousands of such clusters can benefit significantly with this gain. To conclude, we aimed to perform peak shaving without any assumption as done in the prior works. We showed how a data center can be modeled as an MDP. Finally, we showed the feasibility of a policy that significantly outperforms no peak shaving. This demonstrates that peak shaving can reduce the energy cost by up to 33.9%, as there exists at least one such policy as demonstrated. This work can further be enhanced with better availability of the data, as the data source for resource usage of data centers is scarce at the moment. I'd like to thank you all for bearing with me throughout my presentation. Thank you very much and have a wonderful rest of the day.